So yes, I'd like to tell you about the work we're doing on a new data format that we call ASDF at the Space Telescope Science Institute. Mike Droettboom's actually the one that did the bulk of the work. I'm the one that did the least amount of work on this. And I'm sure many of you are, what comes to mind when something like this is suggested is, why yet another format? Are you guys crazy? Yes, probably, but sometimes crazy is good. So let me spend a little time explaining why we did this. Astronomy has been blessed in having a standard format called FITS for over 30 years now. And it's something that has been a great benefit to astronomy. It allows people to exchange data from lots of different telescopes, and just enables astronomy to be done a lot easier. On the other hand, because it was developed so long ago, it has a lot of limitations, and these limitations are making it life more and more difficult for the software we have to develop. And in developing the software pipelines and data analysis for the successor telescope to the Hubble Space Telescope that's called the James Webb Telescope, we've come to the conclusion that we need something different. FITS is just not up to the job with the kind of data that we have to deal with. So given that, I don't have time to go into the details of why that is, but let's take it as a given. That only answers half of the question. So I've only explained why we need a different format. The question is, why do you need a new format? And in particular, why aren't you using HDF5? So I'll spend a little time trying to explain that. There are some actually still very nice aspects of the FITS format. It has two qualities that we want to retain, which I guess I'll call transparency and simplicity. Transparency in the sense that you can see, you can divine a lot about the file by using pretty simple tools, text editors, or just listing out parts of the file, and you can determine quite a bit from that. Simplicity in that it doesn't take a lot to figure out how the data is stored in the file. And so I guess the kind of test I would say is, if somebody came across a bunch of these 100 years from now, would they need any documentation to figure out what was in the files? And I would say probably not. I think you could probably figure out how to interpret the data in the file pretty well from this. Now, I would say what I'm going to describe here with ASDF, I think, is even much better in that regard than FITS is. And so in comparison, I would say HDF5 is neither, really. It's not transparent. It's basically a binary format, and it's quite complex. And I don't think that anybody could easily figure out how to decode the data in the file without the very detailed specification in the format. And even if you did have the specification, you might need to write an awful lot of software to try to figure out and extract the data. So now you might say, is that really important, though? I think based on what we've seen in astronomy, at least for astronomers, it is. They really do, really appreciate being able to see what's in a file easily without having to install software. They may be in a place they can't, they don't have access to the software. And another indication that it's important to them is that although FITS handles tables very well, very frequently astronomers will resort to using text tables instead of FITS tables. It's another indication that they want something that's easy to access and doesn't require them to use software. In addition, this is what we like in addition to FITS, is something with structural flexibility, something that lets us combine things in hierarchical ways and basically construct complicated networks of data if we need to. And there's this aspect of extensibility with validation that I'll talk about a little bit more. As to the first, I think HDF5 does have a lot of structural flexibility, though I'd argue in some respects not as convenient as what I'm going to describe. So in short, I'm looking for something that is a simple format at its root, but can handle complex data and allows you to be able to validate that data fits what you need, what you expect of it. I want to be clear, though, that I'm not saying that this is intended as a replacement for HDF5. It is not intended to give the same levels of performance on very large data sets, at least initially. I don't think there's anything intrinsically, I think with enough work and investment of time, I think most of those capabilities could be put into this, but that's not our priority, and it's, wasn't our goal in this. And the second item I've just mentioned quickly, I'm not really going to explain it, because I don't think it matters in most cases. But finally, what I'm getting at here is I think there really is a need for a lightweight data format. A lot of the problems that, we have lots of big data coming in, files that might be even terabytes in size, but still astronomers, and I suspect many other scientists, deal with data sets that are not massive and don't require that and would benefit from something that was simpler and didn't require very, very complex software. So I think what I'm saying in the end here is this is a complementary format in some sense to HDF5. So let me outline a bit what this framework, how this format works. Basically, we use text, a YAML, to describe all the metadata and define the structure and interpretation of the rest of the data. We chose YAML over JSON mainly for these two reasons, and primarily for the first one, in that it has this tag feature that you can use to identify what a particular component of the YAML should be interpreted as. And we also use that tag information for applying a validation, which I'll talk about at the end. This format does support binary data. That's critical. Some of the past attempts that are based on text formats didn't do this, and this makes them pretty much useless because handling binary efficiently is very important. So this text, this YAML segment can be followed by an arbitrary number of binary blocks. And finally, we're using JSON schema to define the requirements for the various standard objects in this file format. And this is used to validate the files using a validation tool. So the next slide just shows a simple schematic that illustrates what I've been talking about. A file consists of up to three parts. The first part's simple one line that indicates that it's an ASDF file. It's followed by the YAML content, which we call the tree, and it's followed by an arbitrary number of binary blocks. I'm going to show a simple example. I don't have a lot of time to show a lot of more complex examples, but this sort of corresponds to what I showed previously. You see the one line at the top indicating it's ASDF. Followed by YAML, indicate which version of YAML it is. The percent tag there is a reference to where one can find information about the tags that are used in the rest of the document. This particular case only contains one attribute, and that attribute references a simple 2D array. So what you see there is, after my array, is a tag that tells it this is to be interpreted as a multi-dimensional array. And then that source 0 says the data is actually stored in binary block 0, and the rest of the attributes indicate how that binary data is supposed to be interpreted as an array. That you see the delimiters for YAML, or there's dashes and the periods at the bottom. So what follows is a binary block, which starts with a small header, binary header, and then at the bottom, at the end of that header, you'd see the data would be contained in the rest of the block. Now, you don't have to use binary. This particular example could use an inline array. And so this illustrates how you could, if you have small amounts of data and you don't want to use binary, you could just simply put the values in line in the YAML. This essentially corresponds to the previous example, and you can do this with tables as well, because I'll talk about some of the major elements in the format. So it supports complex numbers, n-dimensional arrays, including structured arrays, so that's how tables would be stored in this format. We have support for physical units as standard objects. And the next two items I may speak a little bit more about, because this is actually what gave us the most problems in using the FITS format. It's important for us to be able to associate the array indices with physical coordinates on representing the data. So if, let's say, it's an image, we need to understand which part of the sky, you know, the exact coordinates in the sky that index corresponds to. And our requirements are pretty stringent. We typically need accuracies of hundredths of a pixel. And so for raw data, we often have very complex distortions that involve several transformations. And so we have a fairly complicated model of how that index maps to physical coordinates. And that's part of the format here, is it allows you to do that mapping in very flexible and general ways. So the last item is more of a quality, and I wanted to explain that a bit more as well, which is we wanted something that was extensible. One of the things in FITS was it was very hard to deal with expanding the capabilities without going through lots of hoops. Here, what we've allowed is basically, if you come up with a schema, let's say you're your own project, you can define your own schema and publish it basically, and you can put out files with specialized objects in the file that people can use the generalized validator to check to see if their files meet that criterion. So if you have software that requires that, they can use that validator to make sure they're in the right format. So this is, we thought, was an essential part of making this extensible format. And the reason I'm giving the talk here instead of the astronomy session is that I don't believe there's anything in this general part that I think is specific to astronomy. It seems to me that all these kinds of capabilities in a format are fairly general and useful in many different fields in science and engineering. So we've come up with we have a few tools. So implicit in this, we do have an initial implementation of this. So I'll give you a pointer to that. And we also have a couple tools ready that can take an ASDF file and essentially explode it to make it easier to deal with the components. So what the exploder does is take the YAML, fire it out, and put it in a separate file, and take all the binary blocks and put them in separate files so that you can use other tools if you wanted to get at those components. And we also have the validator that's available that can apply the schema and verify that any given ASDF file meets the schemas. So what are the things that may be coming up? So we're very interested in getting feedback on this. Again, if there are other people that are interested in using this, we'd like to hear what about it would need to be changed or added to make it more generally useful. We'll soon have a converter that embeds FITS into ASDF in a round-trippable way. And most of the tools are there already. It's just not available as a utility. And I want to be clear, that doesn't imply you can just put any ASDF file in a FITS format, because the format's not general enough to handle all the possible structures. And we'd like to develop a conversion utility between ASDF and HDF5 and vice versa. We're looking at doing a C implementation and possibly a JavaScript read-only implementation. And my last slide, give you some pointers to more information. There's going to be a paper in astronomy computing that will go into a lot more of the details of the format and the motivations behind it, and comparisons of various, the advantages and disadvantages of various formats that we considered. There's a draft standards document and Python implementation available on GitHub. We will be using this to support data from the James Webb Space Telescope, which is planned for a 2018 launch. And again, we're very interested in getting feedback on that. And so that concludes my talk. I appreciate any feedback that you have and any questions. Thank you. So the way that's done is we support lots of essentially functional models that allow you to use various kinds of mathematical functions, polynomial transformations on coordinates, plus various utilities that allow you to join, I won't go to the details, that allow you to concatenate multiple dimension things and rework orders of coordinates so that you can pretty much express any coordinate transformation. And if we need to extend it with that more functions, we'll do that. So sort of implicit in that is sort of a general support for a mathematical transformation of any kind, not just for coordinates. Oh, you have a question? I didn't quite hear that. Yes. The question is, do I see any challenges in converting between this format and HDF5? Yeah, I don't think it's entirely trivial to do general transformations. It turns out that, for example, implementing sort of arbitrary dictionary structures in HDF5 is a bit clumsy and wasteful space, but that's doable. I think going the other way would be more complicated in that, you know, saving all the possible variations of how data is stored. And my initial guess is we would, in a first version, throw all that away. You know, so if it's a chunked array and does this, that, and the other thing, we just may make it a simple array. And then in the future, we may add more support for things like that. No, I don't think we're going to promise we'll handle and retain information about every possible, detail of the HDF file. Okay. There are some, okay, I'll go with the one in the very back there.
I was curious about compression and chunking.
No support for chunking yet. There is compression, a couple of compression, zlib and I think bzip 2, all free of licensing issues. Chunking is something that, you know, would be nice to have, but I don't think we'll have it real soon. I think we'd want to see some substantial use before, you know, we added that. Yes.
So I have an issue where I have formats coming out of the model. I need metadata to read them in, but I sort of metadata file next to it. But then when it gets moved around, I get lost. The use case of maybe sticking that YML file in here and just putting that as a binary log, then exploding it when you need to read it, be something which might cause this.
Is the question whether or not you could sort of put an opaque binary blob in with...
I already have a reader that can read that binary blob, but I don't know the binary needs to be read with that.
Yeah, I could, you know, I could see adding a type just saying, don't worry about the contents of this, just read out the binary. I mean, you know, the sort of, the old Python way would have been treated as a string in the old situation, a byte array, and let something else deal with it. Yeah, I don't see that would be a problem. Like,
So for the YAML reader, are you doing like some sort of strict definition of YAML? Because one issue that has come up with YAML is that based on locale, certain values get interpreted differently, such as trues and false, yes, no's, things like that. They automatically
I would have to say, this is a question for Mike to answer, and he's not here. But, you know, I think they give those kind of things serious thought. For example, security issues. We don't use the highest level of the YAML library so that arbitrary objects can be created. You know, so, but as far as locale, I'll have to ask Mike about that. Any other questions?
Do you have any plans to foster uptake of this other than the Pi ASDF, like pull requests to SciPy.io or something upstream?
If people are receptive, yeah, there's a bit of a chicken and egg. We'd like to get a little experience using it ourselves, and so there's always this issue of trying to spread it too widely. You want, you know, I always feel that you want to get some users so that you can get feedback, but not too many that people are upset and think it's unworkable. So you want to go through a couple generations of expansion. All right, thank you.
Thanks, Barry.